Okay, so there wasn't an actual example. I didn't think there was, but I just plugged some numbers in using this equation so that you could see kind of how to mathematically figure it. So say for example, you have someone that has a mass of 75 kilograms. Okay, well, we said that the force of the spring was equal to the force of gravity. Well, force of gravity is mass times gravity. So 75 kilograms times 9.8 is going to give you a force of 735 newtons. Okay, that's normal. That's assuming that everything's at rest, there's no acceleration. This previous slide said that they were accelerating upward, okay? So they said if that was the case, then you could use this equation. Now you could have that the spring force was equal to mass times gravity plus mass times acceleration. Okay, so that would then be 75 kilograms. I should have written it on below. It's okay. Times 9.8 meters per second squared plus your 75 kilograms times the acceleration, which it didn't actually give an acceleration. I'm just going to say 2 meters per second squared. Okay, so if you do that math, you should get 885 newtons. So if you start to accelerate upward, then that spring force is going to show on the scale a higher value. Because if you think about it, when you're on the scale, or just think about being in an elevator, when you're going up, your body kind of pulls down. So that spring force would then, it would be compressed more, which the value then would make the spring greater than. So that is what our quick check is here. It's saying that a 50 kilogram student who has a weight of 490 newtons gets in a 1,000 kilogram elevator at rest and stands on a metric bathroom scale. And it says as the elevator accelerates upward, the scale would read what then? Well, would it be the same? Well, no, because it's accelerating upward. And based on the example that we just did, we saw that when it was normal, it was 735, and when it was accelerating upward, it was 885. So what should that say to you then? That it would be greater than 490 newtons. And this is like almost the same question. It says, again, that this 50 kilogram student gets in a 1,000 kilogram elevator at rest. And by the way, something like this right here, is that actually used for anything mathematically? No, it's just throwing numbers in there. So, again, that's what physics does sometimes. It kind of tries to throw stuff in there. Don't let that confuse you. And it does say again that it's accelerating upward. So now it's just saying that the student's weight is. Well, the student's weight is dependent on the situation. So the weight is greater than 490. Doesn't mean that their mass is greater. It just means that their weight in that situation when they are accelerating upward is greater. Okay, it would be as if they went to the moon, only opposite, because here their weight is actually more. Okay, and now this is showing you the same equation. Okay, that's the one that we just used. And it's showing that an object that is accelerating then downward is negative g, and that weight is equal to 0. So when an object is in free fall, then it has no weight. So think about if the elevator is going down now, your body starts to pull up, okay? And so your weight actually becomes less. And if the elevator in turn, breaks, the cable breaks, and you're in free fall, then there would be a moment in there that you would actually be weightless. You would still have the same mass, but you are considered weightless during that time. So astronauts, when they're orbiting the Earth, they're considered to be weightless and in free fall. Okay, so this says that a 50 kilogram student gets in a 1,000 kilogram elevator at rest and stands on a metric bathroom scale. Sadly, the elevator cable breaks. What is the student's weight during the few seconds it takes to the student to plunge to his doom? So in that case, that would be like I was saying, where they would be in free fall, right? You could do it where you have your, I was thinking of something, but that's more confusing. So whenever you are in free fall, you would be considered weightless, okay? And then in this situation, a 50 kilogram astronaut is orbiting the Earth in the space shuttle compared to on Earth. What is the situation here? Okay. Mass doesn't get less. We know this. Mass is the same. So which one of these situations is the same? They're orbiting the Earth. So is his weight less? Is it the same, or is it zero? Well, when they're orbiting the Earth, they're considered to be in free fall. So his weight is actually considered to be zero in that situation. Okay? You have to have, you have to be in a situation that is experiencing, gravity, So, all right. We are finally in friction. So this is showing different situation. Well, actually, it's the same situation with a shoe that's on an incline, kind of like the car that we saw earlier, a few slides before. And so these two surfaces are in contact, and it's saying here, this is showing like a zoomed in view, saying that very few points are actually in contact, but the molecular bond formed between the two materials have to be broken for the object to slide. So this is saying that a shoe pushes on a wooden floor but does not slip. Okay, and so they're experiencing static friction. And static friction is just a result of basically molecular springs. You can see these little springs here that are being compressed or stretched depending on the situation. And, if it goes too far, then they'll break and then you will slide. Okay? So this figure is showing a rope that's pulling an object that's at rest. And due to the static friction, that box is at rest. It's not moving. So in that situation then, what sort of free body diagram are you looking at? So it says in the second bullet point here that if you look at this free body diagram over here, you've got this tensional force that's pulling it. You've got this frictional force. Does it look the same size? It does. And of course, the normal force and the gravitational force are the same. It's on a flat surface. There's nothing going on there. It's not accelerating upward or anything. So in this case, the static friction is equal to the tension. And as stated before, frictional force is pointing in the opposite direction to the way that the object would move. Okay? And this is showing that it can increase. Okay, so the tension is up here. These are even in all cases, but it's pulling a little. Here it's pulling a little bit more, and depending on how much static friction there is, and then it gets to the max. And once it reaches that frictional max, if the tension gets any bigger at all, then the objects will start to move. So in this case, it's showing that a box on a rough surface is pulled by a horizontal rope with tension T, and the box is not moving. So if the box is not moving, then what should that tell you about the two? That they are, at that point, they're equal, okay? They're in equilibrium, essentially. So, all right, I'm gonna stop the video again and start up again.